Welcome back to navigation. We're going to take a look at the chapter on convergency and conversion angle. Let's take a look at convergency first. Now, we know that the meridians are parallel to each other at the equator and they converge at the north and the south poles. Now, I've got a diagram drawn up. It's a three-dimensional representation of the Earth, North Pole over there, equator over here, meridians over here. I've also drawn up some tangents to the meridians at A and B. Okay, so the distance between the two meridians is largest at the equator and it converges towards the poles. Alright. I have not shown the south pole over here, but it doesn't really matter. You can imagine it. Now, convergency is defined as the angle of inclination between any two selected meridians measured at a given latitude, and it is given by the formula convergency is equal to change in longitude or difference between the two longitudes in degrees multiplied by the sine of latitude. Now, why the sine? Remember, we spoke about how at the equator there is no inclination between the two meridians. Alright, therefore the sine 0 represents zero inclination, while the inclination at the poles is maximum, therefore 90 degrees representing sine 90 equals to 1, showing us that the inclination is maximum at the poles. Alright, therefore we use sine. So, because of the inclination being least at the equator and the angle of inclination being maximum at the poles. Okay, if you want, you can have a read of this. Alright, what I want to point out to you is over here I've got the angles written down and the sine values of it. What you can see is at sine 30, the inclination between the two selected meridians is 0.5 or 50%. At 45, 70%, and at 60, 86%. So the inclination increases from the equator to the poles from 0% to 100%. That is what convergency is about. Okay, so why do we need to understand convergency? It's very simple. We are in the pre-flight planning section, okay? And the convergent nature of meridians causes a change in direction. Alright, understanding the value of change will help us to plan better, make adjustments during pre-flight, and therefore it will help us reduce the in-flight workload. Alright, now this will also help us confirm correct planning and progress in line with DIID. Do you remember DIID? We learned it in the second chapter and it tells us about the change in direction when we are heading east or west in the northern or southern hemispheres. Alright, in this case, we will be heading from 25 degree west to 25 degree east in the northern hemisphere. The compass numbers will increase. Okay. Now, we spoke about a change in direction. How does this change in direction occur? It's very simple. I have the northern hemisphere of the Earth drawn up, okay? The North Pole there, equator here, 25 degree west, 25 degree east, meridians drawn up. We will be heading from a place on the 25 degree west meridian A to a place on the 25 degree east meridian B here. Having drawn tangents at both points, we can measure the angles. Now the angle at A is shown by blue, the angle at B is shown in black. I've expanded it over here and I've transferred the tangent over to B. Now, the measurement at A, the angle at A is represented here and the angle at B is over here. You can obviously see that there is a difference in these two angles. This occurs because of the convergent nature of the meridians with latitude, right? This difference in angle is called convergency. This convergency, when it is known, it helps us to plan better and therefore it reduces our workload in accordance with DIID. Alright. Now, next we are going to take a look at conversion angle. This will help us understand how to convert between Rhumb line track and great circle track, especially using convergency. So, what is conversion angle? It's the difference between the Rhumb line direction and the great circle direction joining at any two given points. Right. It's given by the formula conversion angle is equal to half of convergency or half into change of longitude in degrees into the sine of latitude. Here I've drawn a Mercator projection. So the meridians are parallel to each other and therefore the Rhumb line track has a constant angle, as you can see. The great circle track is obviously curved towards the nearer pole. In this case, 40 degrees north towards the north pole. What you can see here is the great circle track angle shown in blue and the Rhumb line track angle shown in red. The difference between the two of them shown in green is the conversion angle. So all of this is great, okay, but the thing that we've missed out majorly is the fact that we have seen all of this on one single latitude. What if your departure is on one latitude and your arrival is on another latitude, what happens then? It's very simple. The formula then changes in a very simple way. Convergency becomes ch long, or change in longitude in degrees, into the sign of middle latitude or mid latitude. Conversion angle then becomes half of convergency or half of change in longitude in degrees into the sign of the middle latitude. What does that mean? If you were to depart at 20 degrees north and arrive at 50 degrees north, you would take the difference between the two, which is 50 minus 20. So 30 degrees in between the two, and then divided by 2, which will give you the middle latitude. Alright. In this case, 15 degrees, which is either subtracted from 50 or added to 20. Okay. Now, why do we say middle latitude? It's very simple. Again, you need to consider the latitudes between the departure and the arrival latitudes. Alright. It can happen that you depart from the southern hemisphere and arrive in the northern hemisphere, or vice versa. Alright. In that case, you need to understand that the difference between the two needs to first be found out, then divided and either added or subtracted as required. After this, we'll take a look at a couple of problems. Alright, so this is what a typical question looks like in the examination. If you travel from A to B, coordinates are given with an initial GC track of 082 degrees to answer the following questions. There are 7 sub-questions in there which are typical of this type of a question. Now, the first thing you need to do is remember that there are 3 bits of information given. Write them down. Alright. Now, take a look at the coordinates of A and B. It says 030 degrees north, 030 degrees north. It means that it is on the same latitude, which means that we need to draw a diagram that looks like this. Remember that drawing up a diagram with the meridians as parallel lines helps us get a nice strong rhumb line. Alright. And that just means that we get a curved great circle. Coordinates for A and B are here. You can see that they are on the same latitude, which means that the rhumb line track is the same as the latitude. Alright. So rhumb line track from A to B is 090 degrees to, answering the first question, and rhumb line track from B to A is 270, which is the reciprocal, answering question number B. To answer question C to G, first we need to draw up this diagram. This is the Earth drawn from the top down, with the North Pole in the center, east and west, left and right, 0 degrees meridian over here. Now we're going from A to B, 1122 is 080. This is what it will look like. Alright. And when you look at it in this direction, this is exactly what it will look like. Okay. Now, the formula for convergency is convergency equals change of longitude in degrees into the sign of latitude. We already know what latitude we are on, and the change of longitude is basically the number of degrees between 112 and 080. Alright. This comes out to 32 into 0.5, which is 16 degrees. This is your convergency. Now we know from the formula that conversion angle is half of convergency, therefore it comes to 8 degrees. Okay. Now, when we want to convert rhumb line to great circle tracks, we need to use this 8 degrees. Okay. How? Very simple. DIID first comes into play. You're in the northern hemisphere and you're going from west to east. Flying from west to east in the northern hemisphere, directions will increase for great circles. You can see it is 082 over here. Okay, plus another 8 degrees, that will give you 090. So this data is correct. Therefore, conversion angle is correct. Therefore, convergency is correct. Now, we've got the initial track. We want the final track. Final track is here, past 090. By how much? 090 plus conversion angle. So, 098 degrees. True. This is your final GC track. Now, initial GC track from B to A. Now we reverse the entire program. Okay, what we do is we are going to go from B to A. When you're going from B to A, what happens to great circle tracks? They start off that way and they reduce. Therefore, your initial great circle track needs to be larger than your final great circle track. That will help you understand whether you have done the problem correctly. Now, initial GC track, you need the rhumb line track from B to A first. Do you know what it is? It's right here. 270. 270 plus 8 degrees. Why? Because 270 and we're turning to the right, that's where the great circle track is. So you add 8 degrees over there to get 278 degrees true, since rhumb line plus conversion angle equals to great circle track. final GC track is again extremely simple. All you need to do is remember you are now flying this direction. Okay, so 270 is over here. You're turning towards the left, therefore you will subtract how many? 8 degrees. 270 minus 8. That will give you 262 degrees. Alright, that's all the answers that you've got over here. And it's very simple. All you need is one Rhumb line track and initial or final great circle tracks. Okay, and you can solve the entire 8 questions together. It's easy.